and welcome everybody to the first of 2025 webinar from the UK Freshwater Quality Research Programme. Yeah, as Finn said, I know lots of you have joined these before, but as always, there's new people. So just going to give you a quick overview of the programme. It's funded by NERC, Natural Environment Research Council, and DEFRA. And the objectives of the research programme are on this screen here. It's really to strengthen our understanding of the sources, the behaviour of pollutants within our freshwater systems, understand how we can reduce the pollutant load and how those pollutants have an impact on our freshwater ecosystems. And really importantly, we want to ensure that this research is used by policymakers and those in the industry, and really allow us to adapt and mitigate the risks of these pollutants and improve our freshwater ecosystems. So within the programme, there are 5 research projects, and those research projects are listed here. And this year, we've already heard from them once last year from the PI on the programme, but this year we're going to hear from the early career researchers working on these research projects. And today we're going to be hearing from EcoMix, which is the project at the bottom, which is led by the University of York, along with the University of Sheffield and Durham. And they're really looking at assessing and managing the impacts of mixtures of chemicals on UK freshwater biodiversity in a changing world. And so these webinars are monthly, and there's a whole range of ways you can engage with us. We have a newsletter as well. You can register for that. You can register to hear about the other webinars. As Finn said, the webinar itself is recorded, so you can catch up with them on our website. You can email us, freshwater@leeds.ac.uk. We are the champion team for the programme. We oversee the programme, and you can follow us on social media. So before I hand over to this today's webinar, just to give you a flavour of those that are coming up. So I said we'll be hearing from the other 4 of our projects over the next 4 months. And here are the dates to hand. So our next one will be on February 17th, where we'll hear from MOT for Rivers, which is really looking at, we'll hear about that. So I'm going to hand over to our 3 early career researchers. So we've got Martha from the University of York, Amy from the University of Sheffield, and Ivo from Durham University. So over to you, Martha. Great.
I need to unmute myself now. It's okay. So good afternoon. My name is Martha, and I'm based at York. My co-presenters are Amy at Sheffield and Ivo and Durham. And we will provide an update on the work carried out in the last year. EcoMix is a collaboration project based at York with Durham and Sheffield as partners. And then we have a number of associated partners involved in the project, which are shown at the bottom of the slide. So we all have heard about the poor state of UK rivers. So I have a couple of photographs here. So you see here at the top, there is Ilkley, which is a very popular bathing site in the Wharf. And well, we have seen signs advising people not to get in the water due to water pollution. Then more recently, here at the bottom, so this is news from last week in The Guardian, the High Court had ruled that the government has not met a legal duty to clean up the Costa Beck near Pickering. So according to this article, this is a former trout stream that has been devastated by sewage pollution and runoff from fish farms. So as we know, no single stretch of river in England and Northern Ireland is in good overall health, and only 15% of rivers in England are judged as having good or above good ecological health status, mainly from rural, wastewater, urban, and transport sectors. So we know that freshwater and wetland species are in decline in inland rivers, and then some of these species are threatened with extinction. And Underwater Framework Directive, which is part of British law, all water bodies should achieve good ecological status by 2027. So this is the problem that we want to tackle. So our rivers are under a cocktail of hundreds and thousands of chemicals, and previous studies have mainly focused on a small number of chemicals, mainly from single sources. So our project would like to move into the impact of chemical mixtures on species, looking at all sources. So just to remind everyone what our project is about, so we want to develop a new catchment-driven approach that considers the impacts of chemical mixtures and co-stressors on a species at a high spatial resolution. We would consider current conditions, but also we want to look at future. So what are the impacts of global megatrends on how we use chemicals, the fate processes, exposure, and effects on species? So this will allow us to target interventions where they're going to have the maximum impact. So we will explore a range of different mitigation options, such as changes to land use or management, moving into more nature-based approaches, or introduction to engineering solutions, such as upgrading wastewater treatment plants. So as we move forward, we would like to improve the quality and biodiversity of our rivers. So this project is a 4-year project, so we are halfway through now. It's being delivered in 6 work packages shown here. So work package number 1 is where we identified our study chemicals. Then we have a series of work packages working in tandem. So in work package number 2, we want to understand current and future chemical use in the region. For package 3, we look at modeling and monitoring of mixture exposures. Here is where we generate our exposure profiles. For package number 4, we begin to understand the effects of those chemicals on the species. And then those data will be fed into work package number 5, where we have our ecological effects modeling. And this will help us to identify hotspots of risk and what is driving that risk. This will allow us to move into work package number 6, where we would identify how we're going to mitigate the problem. So adaptation and mitigation strategies, as those that I already mentioned. So throughout the project, we are working with the stakeholders and partners, for example, like we did for the chemical selection through a series of workshops. We also work with partners in the design of the monitoring program. We have volunteers that help us operate the auto samplers and collect samples. We also work with our partners in the emission modeling of chemicals, so they have provided valuable input model data. So my part of the presentation focuses on work packages 1, 2, and 3, so the chemicals, the monitoring, and the modeling. So this is work that we presented last year. These are our priority chemicals. They include pet medicines, pesticides, livestock medicines, pharmaceuticals, like for example, metformin, which has a drug for diabetes. We also have preservatives used in personal care products and UV filters. Finally, we have pHs, metals, and tire additives like 6-PPD, which has been associated with the death of salmon in the US. So this is our study catchment. It covers most of Yorkshire. It includes 9 major catchments. This is an area of 10,700 kilometers square with a variety of topography, land use, climate. So for example, in the northwest, we have the Yorkshire Dales, where we have our uplands, rural towns, where there is a higher livestock density. In the northeast, we have the Yorkshire Moors, National Park, where we have mainly arable land and some marker towns. So towards the middle and the south of our catchment, we have the large cities and industries. So we have Leeds, Sheffield, Bradford, Huddersfield. So this is work that we also presented last year. So we generated these source density maps that help us to understand our sources of chemicals, and they also helped to identify the locations for our autosamplers. So this is new work I'm presenting here. So we have been running a continuous monitoring program for the last 9 months. So we installed a series of 19 autosamplers in 10 rivers. And here is a map of our monitoring sites. And we take weekly composite samples that are collected by our volunteers at 11 sites. And we also collect ourselves, we collect at 8 sites. And I would like to take this opportunity to thank all our amazing volunteers who help collect samples and to the hosts of our autosamplers. So here are some photographs of our rivers and autosamplers. So we have a variety of river sizes. So we have large rivers like the Ouse Marina, the small rivers like the Rye. We have some turbid rivers like the Wiske and the Foss. We have some heavily modified rivers, like the Chief near Sheffield and the Aire in Leeds. We have more natural rivers like the Derwen at Hoxham and the Swale. So the group at York developed analytical methods for 53 organic chemicals, shown here. So we're using liquid and gas chromatography. These include our priority chemicals and some of the CH project LTLS, which is also included in the freshwater quality program. And I color-coded chemicals here as they are going to be grouped in the next slides. And just also to mention that we were not able to measure, to include analytical methods for mectins and a couple of our methrines that gave us problems. So delta methrin and cypermethrin were not included. And here are some results from our monitoring program. So here is a graph of total organic chemical concentrations by sites. And this is showing data for the first 5 months from LC and the first 3 months for GC, and this is mainly from the methrines. And here on the left, I have created this map with a ranking of the sites with the highest total organic concentrations. So we found that the highest concentrations were found in the Calder at Wakefield. And this is followed by the Aire at the confluence with the Calder. Next is Leeds, so the Aire at Leeds, and followed by the Calder. This is downstream of Huddersfield. Then we also observe high concentrations in the Foss in York, followed by the Wiske, the Derwen Upper, and then we have lower organic concentrations in other sites. And then the less polluted rivers were the Swale. This is upstream of Richmond. And we have the Rye at Nuneaton. So these are more results from our monitoring program. So you can see the detection frequency of organic chemicals in this graph. So we found pharmaceuticals in all the samples, in all the sites. Metformin was found in all the samples, and normally it was the one with the highest concentration. We also have had high detection frequency of antibiotics, here in blue, anti-epileptic, this carbetamide. Then we have antihistaminic cetirizine. And the most detected pesticide was trialate. And in the left is a map of the ranking of maximum number of organic chemicals detected out of the 53 chemicals that we analyzed. So the site with the most complex mixture of chemicals was found in the air at the confluence with the Calder. This is followed by the Derwent Upper, and this was a surprising result. And this is mainly due to pesticides. And then we had the Calder, followed by the Foss. Then we have the Whisk, the Foss Upper, and the Ouse. And all the other sites show less complex mixtures of organic chemicals. And the sites, the less polluted sites were again the Swale and the Rye. So in terms of modeling of river concentrations, we are aiming for a high-resolution system-based mixture exposure model of chemicals and co-stressors. So in general terms, our model input data includes catchment data such as land use, soils, population, pet population, point sources, road traffic, just to mention some. Then we use chemical usage data, so we use the best we could find for our catchment. So we use monthly NHS data at the GP level. Then we have pesticide data, the 10-day resolution for Yorkshire. We have national sales of livestock medicine, annual industrial discharges from an EU's database for the UK. And this data is fed into our river flow and chemical emission models. So HYPE is our hydrological model, including some water quality parameters. Then we have a series of emission models that we developed for point sources and diffuse sources. So the river flow and emissions are then fed into our DELF3D model. So this is a model that routes the chemical down the stream. And we selected this model because it includes a good description of in-stream processes for all chemical types. So the group at Durham set up a HYPE model with 16,500 subbasins. Well, these are not real subbasins, but these are the hydrological units in HYPE, with an average spatial resolution of 50 hectares. Here are some results from HYPE. On the left side, you can see hydrographs for all of our rivers and compared to the observed. And HYPE is able to model both high and low flow periods with a good model efficiency. So acceptable levels for discharge for river flow, is NSE of 0.7, and we were able to get an efficiency of 0.8 to 0.9, so very good. And then on the right, you can see water temperature modeling from HYPE, which also show good results against the observed. And now moving into the modeling of emissions. So here is an example of one of our models. This is the wastewater treatment plant and CSO emission model that we created. So this one, we have used it for all our down the drain chemicals. So we work with our partner, Yorkshire Water. So they provided some input data like flow to full treatment. So that's the capacity of the plant. The dry weather flow, so this is the sewage that's generated daily from domestic and industry sources. And then the difference between the capacity and the dry weather flows is the storm capacity of the plant. So what we assume in our model is that when there is a heavy rainfall event and the storm capacity is exceeded, we have a CSO discharge. Then we also use wastewater treatment plant catchment maps to estimate how many people are connected to the treatment plant. So our model includes 500 wastewater treatment plants and 1,800 CSOs. And here is some model evaluation looking at the spill count compared to the observed, and we were able to model most of CSO discharges. So here are a couple of examples of our emissions map that we obtained. So the points represent the emissions at the wastewater treatment plant combined with the CSO for one antibiotic, azithromycin, where you see highest annual emission concentrations at Leeds, Huddersfield, and Sheffield. And similarly for one of our metals, zinc. So we have high emissions at Leeds and Sheffield. Then we are also using chemical investigation program data to evaluate our models, and this is effluent concentrations. So the blue is the observed concentration and the red is the model. So in this case, our aim is to be able to model emissions and river concentrations within the same order of magnitude. And so this is within a factor of 10. And I'm showing here Nostrop is Leeds, where we were able to predict within a factor of 2. Then we have Nailey that is in the south of Huddersfield. There is a bit of model under prediction, but still within a factor of 6. And then Garford, that's east of Leeds, within a factor of 2, and Lemonroyd, a factor of 2. And here I'm showing results for zinc from wastewater treatment plants, where we also found acceptable levels of our model, with again some under prediction at Nailey. So with this, I hand over to Amy, who will talk about the effect of chemicals on a species. Let me see. Yeah. Amy, can you see?
Hi, yeah. Okay, hi everyone. Thanks, Martha. My name is Amy and I'm a postdoc at the University of Sheffield. So for the next part of the presentation, I'm going to talk to you about our work on how we've assessed the effects of chemicals on UK relevant species in Work Package 4. I'll then move on to talk about how we're planning to scale these findings to entire freshwater assemblages, taking into account combined effects of mixtures, interacting species, and varying environmental conditions. So Work Package 4 focuses on assessing the effects of high priority chemicals on freshwater species, and our project is centered around two key groups, that being freshwater invertebrates and freshwater algae. So these groups are both important to the health and functioning of freshwater ecosystems, and both are particularly vulnerable to freshwater pollution. So the rationale behind this work package is that current ecological risk assessments only focus on a limited number of chemicals and a limited number of species. And given the large number of species, given the large number of chemicals in use and the diversity of species, it's not feasible to conduct toxicity tests for every chemical species combination. So our objective is to come up with a quantitative or systematic approach to predict or extrapolate species toxicity based on a chemical's toxic mode of action. And what we mean by a toxic mode of action is the specific biological processes or mechanisms through which a chemical causes harmful effects on an organism. So as I previously mentioned, most risk assessments focus on very few species, often just a single species like Daphnia magna. But in reality, freshwater ecosystems are extremely diverse and they vary taxonomically and functionally. So for our work on the invertebrates, we chose to test the effects of chemicals on 9 different invertebrates to better capture this diversity. So they vary taxonomically and functionally. Same goes for the algae. We wanted to capture as much taxonomic diversity as possible. So for this, we're focusing on testing the effects on 12 freshwater algae species, including green algae, blue-green algae, and diatoms. that all vary taxonomically and also have different physiological and morphological characteristics. So Martha showed this slide previously, which is highlighting our priority chemicals. And I've just highlighted here the different types of chemicals we're testing on invertebrates in blue and algae in green, and both the invertebrates and algae in purple. But from these high priority chemicals, we wanted to determine whether the toxic mode of action could be used to predict toxicity through read-across methods. So to do this, we selected 12 different chemicals, and the chemicals here refer to the ones tested on invertebrates, but we applied the same methodology to the algae using a slightly different set of chemicals. So for this, we focused on 4 chemical groups, each representing a different toxic mode of action. So a group of insecticides, 2 groups of fungicides, and then the polyaromatic hydrocarbons. And within each group, we tested 3 structurally similar chemicals. Then the species were exposed to a range of concentrations, and then we measured mortality for the invertebrates or growth for the algae. And then from this, we can generate what's called a dose response curve, which is looking at survival against concentration. And these can be used to calculate EC50s, which refers to the concentration at which 50% of the individuals are affected. And our prediction was that within a certain toxic mode of action, so within a group of chemicals sharing the same toxic mode of action, while the overall toxicity level of the chemicals might differ, the rank order of species sensitivity remains consistent. For example, this diagram here, we have species 1 to 7, representing different species. And then if we test the effects of chemical A, for example, and then we produce a certain pattern of species sensitivity, if we then test chemical B or chemical C, although the toxicity of the chemical may differ, we expect the relative pattern of sensitivity across species to remain the same. And if this prediction holds true, it could reduce the need for future experimental testing, as we would be able to extrapolate species effects from one chemical to the other. So for the invertebrates, what we found was that species sensitivity depended on the specific chemical being tested. So this matrix here shows species on the y-axis and chemicals on the x-axis. Yellow squares showing the least sensitive and blue squares showing the most sensitive organisms. And this basically highlights that sensitivity is chemical specific. For example, mayflies, for example, might be really sensitive to insecticides, but less sensitive to polyaromatic hydrocarbons. We also found that species sensitivity depends on the toxic mode of action of the chemical. So this matrix here shows all the chemicals that we're testing, and it's basically comparing the rank order sensitivity of chemicals. So each one of these little squares here is comparing the rank order between 2 certain chemicals, for example, deltamethrin versus permethrin. And the ones highlighted in black are comparing the groups that share the same toxic mode of action. And the red color highlights a high level of similarity across species. So what we find is that rank order of species sensitivity is more similar within chemicals sharing the same toxic mode of action. And this predictable sensitivity pattern suggests we can target ecotox assessments, and this reduces the need for extensive chemical testing. Now, the algae work is a little bit behind the invertebrate work, but we're starting to generate a similar kind of matrix of species chemical combinations. So the brown box showing the diatoms, the blue box showing the cyanobacteria, and the green box showing the green algae. And once we start to populate this matrix, we can ask the questions, do different freshwater algae show different responses to certain types of chemicals? Is it taxonomy, or are there certain traits that render a species more susceptible? And like the invertebrates, does the rank order of sensitivity of different species to toxicants remain consistent within a toxic mode of action? Now, one final part of work package 4 that we're going to be working on is understanding the fact that chemicals can cause more than just mortality in invertebrates. They can also cause sublethal effects, like affecting the way organisms feed. So to explore this, we're looking at 3 different feeding interactions. We're looking at a scraper-diatom interaction, a shredder leaf material interaction, and a predator-prey interaction. And we want to then test whether the patterns we see in the acute toxicity studies hold true for sublethal effects as well. So for example, does the rank order toxicity remain consistent across species when it comes to their feeding? I'll now talk a little bit about work package 5. So the objective of this part of the project is shifting from the focus on just effects on individual species to considering impacts on whole assemblages and ecosystems. So obviously there are still many more species present in UK freshwater assemblages, and we can't test every species chemical combination. So then we ask the question, how can we make predictions about the sensitivity of untested organisms? So what we plan to do is use a hierarchical species sensitivity distribution model, the HSSD model, which is a model that uses both taxonomic relatedness and acute toxicity data. So into the model goes assemblage specific species lists, and then lab toxicity data, which we've generated in work package 4. And then what the model does is it predicts EC50s for all the untested species based on their relatedness. And from that, we can identify the proportion of species at risk from certain chemical mixtures at each of our sites. So the other part of work package 5 is that chemicals can affect species directly via acute toxicity and also indirectly via food web interactions. So the next part of this is to use data generated from both the acute toxicity studies and the feeding studies to model the effects of chemicals, considering the ways that species interact with each other. And then we can start to think about how this changes with other stressors, such as temperature, nutrients, or chemical mixtures. And this work package will basically allow us to generate a broader picture of how chemicals affect whole ecosystems. I'm now going to pass over to Ivo, who will introduce the final work package 6, and present our ideas to disseminate our research.
Yeah, hello everybody. My name is Ivo, and I will talk a bit about the research dissemination. So we will produce all these different data sets from modeling, monitoring, lab work, and also from the topics very diverse with water quality, hydrology, and biodiversity. And we're thinking about how we can make this accessible to everybody who's interested, not only academics, but also stakeholders and the wider community. And yeah, we have several deliverables. That is, creating online videos, writing manuals, workshops, but also a web dashboard. And that can be a very powerful tool to interact with our data and visualize our data. Now, one key issue with this is balancing the functionality and the usability. So, as I said, we generate really a lot of data. And the more data we integrate into this tool, the higher the functionality. But on the other hand, it might get confusing to actually see through it and use it. So we would like to have your feedback on this. So we'll share a link with the form or with the questionnaire. It's only 5 questions that shouldn't take too much time to answer, and it's you don't need to sign in or anything. But it would help us to guide the development of this tool. And I'll show you briefly a prototype that we created to show you or give you an idea of how such a tool could look like. So this is the prototype. We implemented it for the WRF for now. And here you can see our spatial units for the hydrological modeling part. And we can integrate more, such as our monitoring sites. But you can interact with these features. So you could select, for example, the subbasin, and it would give you some brief information about that area. And then we can move on to further explore our data that we generated for this area. So, for example, we could look at different climate variables, look at the precipitation, for example, the temperature. These are monthly averages for that specific area, but we could also move, or we could also, explore yearly averages, for example. Then we have a plot with monthly runoff. The river stream flow in this area. Here we could also move or create sliders that you can move into specific areas in time. And water temperature. So we can add a lot of variables that we create. And we can also think about or compare projections, because we will run this for the past, or we did run this for the past, but then we also run climate and land use scenarios, so we can compare how these have effects on different components, hydrological or quality-wise components. We could use this tool to access the data and download data, actually. So basically, we can subset variables or areas. And as I said, so this is just a prototype, so we can add really a lot of information about chemicals, about biodiversity. We could create maps that showcase or that highlight specific areas of higher risk or lower risk. So it would be great if you could, fill out the form, give us some feedback so that we can, develop it. And there will be also a workshop that, we will hold or held to develop it. So if you want to be part of this workshop and shape it, then please fill out the form. There will be an opportunity to sign up for the workshop. So I hope I can move to the next slide. Okay, so just to wrap this talk up. So summary of the progress to date, we completed work package 1. Work packages 2 to 4 are well on the way. We are sort of in the later stages of it, but did good progress so far. And then, so what we will do next is, so the river monitoring will be finished by March, so it's about to finish. We will finish the modeling of the nutrients and the concentrations of the current condition within the next month, and then we will start to simulate different scenarios. Future projections, and we will conduct the food web and risk assessment work also in the following months. So here on the QR code is you can scan it for the form, but we also have a link for the questionnaire in the chat. And looking forward to your questions. Thank you very much.